Hi all, my name is Abhimanu, and I'm going to present today Fugue, Slow-Worker-Agnostic Distributed Learning uh, for big data on big models. And it's a joint work with my advisor Eric and my friends and colleagues Alex and Chirong. So what are we dealing here? In this presentation, I'll be talking about mostly big data challenge. And the problem is that we keep generating huge amount of data each day. And we need large-scale ML systems to deal with this, which kind of everybody knows this. But the current large-scale systems have many limitations. So for example, just as to drive this point home, we have 1 billion users on Facebook now. If we want to detect communities, we have to do a tensor decomposition at least on 1 billion users. Then we have 400 million tweets per day. Then we have like Netflix on collaborative filtering, and then we have dictionary learning for computer vision, where we keep uploading photos on Facebook, on Snapchat, and all those things. So dealing with big data towards big ML. So the idea is that we can scale both on data as well as model. And let's, for example, look at this left-hand picture, where we have lots of, we have a corpora of documents, and we want to do a topic modeling. So we have lots of data here. And on the right-hand side, we have distributed neural network, deep neural network, where, for example, we have 1,000 layers of DNN, 1,000-layer DNN, where each layer has at least, say, for example, 20,000 neurons. Then when you do distribution on the DNN, we are distributing on the model. And when we distribute on the corpora, we are distributing on the data. So we can do both, which kind of this esteemed audience knows that. Now, when we go for big ML systems, the way we distribute is essentially, in every kind of ML system, we have this parameter which is being updated iteratively. And the updates which are added to the previous value of the parameter are essentially a function of the accumulation of data, which is essentially, for example, you can divide the data into D1, D2, Dn here, and a collection of parameters, which is, say, for example, θ1 to θk, and you essentially distribute over these two. Now, but we are trying this, like, we want to drive this point home that we need, for big data, we need huge models. An example for this would be, for example, we want to do topic modeling over tweets, and we have, as I said before, 400 million tweets per day. And if we just take 5 days worth of those tweets, those are 2 billion tweets. And let's be modest and say that there are 300,000 words, and we just take 1,000 topics, then that leads to 2 trillion parameters to learn, and that amounts to 7 terabytes of model, and which is essentially just the model. We don't have taken into account the data that comes with, say, 2 billion tweets. So what is the challenge in learning both data and model together? Let's look at the current big ML systems that are out there. We have Vertex Program-based systems like GraphLab and Pregel. We have MapReduce-based systems like Mahout. We have data parallelism systems like Spark. And the challenges that they face is they need to distribute both on data as well as model. The distributed scheme should be theoretically well-grounded, and they should be able to run on clusters with varying capacity of machines, which is kind of important because any run-of-the-mill cluster will have varying workloads on different machines, and they will also have machines with different capacity. So what are the limitations that these current systems face? They do not differentiate between data and model. They have no theoretical guarantees. They are scalable in only one, either data or model, and they are very susceptible to slow worker bottlenecks. I'll talk in detail what I mean by slow worker bottleneck. So we have a solution for this. We come up with a Fugue, with a scheme called Fugue, which is scalable in data as well as model. It is faster since it's not affected by slow workers, and it's very well grounded in theory. Now, to give you a sneak peek of what I'm going to talk about and how performance of our system does, is essentially we are comparing Fugue with two paradigms. One is the Vertex program. An example of that would be GraphLab, and one is parallel stochastic gradient descent, which is an example of data parallelism that I talked about, like a Pregel kind of a system. And we are comparing Fugue on 3 distinct problems in machine learning, topic modeling, sparse dictionary learning, which is SDL, and we have mixed membership network decomposition, which is essentially finding communities in networks. And we see that, in general, Fugue performs 25 times faster than all these systems, and at least 3 to 4 times faster in the closest competitor in the particular problem domain. So you see that there is a significant amount of speed up. Now, before I go much deeper into the talk, I need to give you an outline of what I'm going to talk about. So first, we'll talk about the background. Then we'll talk about what does Fugue does, essentially partitioning, projections, and slow workers, because all these things are involved when you deal with complex ML problems. Then I'll talk about the MapReduce implementation for Fugue, just taking MapReduce as an example. And that's why we call Fugue as a scheme, not as a system, because this can be done on MapReduce or other systems as well. Then we'll talk about results, then the theoretical guarantees that is provided by the scheme, and then we'll recap, and then we'll probably discuss and take questions. Now, let's look at simple matrix factorization. So matrix factorization can be done using sampling, using gradient descent, or stochastic gradient descent. And in case of big data, people generally prefer stochastic gradient descent. So in case of stochastic gradient descent, if you look at two particular entries in a matrix, right? So for example, let's look at the top left corner, which is the red entry, and the top bottom right corner, which is the white one, right? So if you look closely at the equations of the SGD updates for the factors U and V, which you are breaking the original matrix into, then these two different points correspond to two different rows and columns, two different set of rows and columns. Essentially, the red corresponds to the updates on the red rows and columns, and the white corresponds to the white rows and columns of the factors. And essentially, we can distribute these two updates, and it can be thrown into two different separate machines, and they can happen parallelly. So there is this independence property there. Now, this idea can be extended to a block kind of a thing as well, where we partition the matrix in a style where we are partitioning into a block by block style. And for example, for simplicity, if you assume that the matrix is square, then you have and you divide the rows and columns in D parts, then you have a D square block, and you are essentially in every block you are updating different parts of the factors. And for example, the green part of the matrix here is updating the green parts of the corresponding U's and the V's. The red part or the pink part is updating the different rows and columns of the U and V factors, and similarly for the blue. Now, this idea of block programming was exploited by Gemula for simple matrix factorization. In a KDD 2011 paper, for example, they distribute the matrix into D square blocks, and they take one strata at a time. So for example, they take D blocks at a time such that no rows and columns overlap. And then they run SGD updates parallelly on different colors. And then they move on to a next set of D blocks, which is called strata. And then when that is done, they move to next set of D blocks. And essentially, when they cover all the blocks, all the D square blocks in this strata sequence, it is called one epoch. Now, as you can see, there is this distributed parallelization in this scheme. Fugue does this for complex problems. For example, we do this for mixed membership network discovery. We do this for topic modeling. We do this for coupled matrix plus tensor decomposition, which is a common problem in case of, say, you are doing collaborative filtering and you have meta information about, say, user and his age. So how do we do distributed topic modeling? So like as we discussed before, or as I pointed out before, we have this matrix and we are doing a block programming, right? And then, so these updates, the updates for example, a generic theta would be at iteration t+1, the block assigned, the subset of the parameters which are in block I would be updated by the previous previous values of those subset of parameters, plus the block of data that has been assigned to that particular block, and as a function of the subset of the parameters assigned to that particular block. Now, but in case of topic modeling, we have, before I delve a little deeper into this, let me give you a background of what we are doing here. So we have a matrix like word by document matrix, and we are decomposing into a classical topic by document and topic by word matrix. And so we have these different blocks, and those blocks corresponds to these i's indexes. Now, in case of topic modeling, the independence breaks because for example, for the topic word vector, the rows should sum up to 1 because it's a simplex projection. So that's what I mean here, where we need to synchronize across the blocks for the topic word factor, and that leads to problems because we have this heterogeneous group of machines on any cluster, and some are slow, some blocks would be slow, some blocks would be fast, and we essentially need to synchronize between them. So before I delve more into this problem, let's say how Fugue does it. So the high-level algorithm for Fugue is you have 1 to t epochs, as I defined epochs before, and then you have these strata or sub-epochs, and we are essentially dividing this matrix into d square blocks where each strata has d blocks, and there are d stratas. Now we pick sequence of stratas, we run SGD parallelly on every block in that strata, then we do constraints or projections, as I talked about constraints in case of topic modeling, where you have to sum up across the blocks. And then when you have finished all the stratas in one epoch, you essentially, if there are any constraints or projections which need to be applied across the whole spectrum of the blocks, we do that. Now, as we talked earlier about the slow worker problem, Fugue is slow worker agnostic. And the reason why it's slow worker agnostic is that it's a simple idea, but it's also well grounded in theory. So the idea is that the faster blocks or the faster workers need not wait for the slower ones. Instead of waiting, they should do useful work. So what I mean by useful work is that for example, if you're doing gradient descent, they should not take the same step size as they were doing previously, but they should modify their step size to take into account that they are waiting for the slower workers. This useful work leads to a variance decrease when you are closer to the optima, and which is very, very advantageous, as I'll point out in the results section. Now let's look at the Fugue implementation for tensor factorization. So we have a tensor, and we are decomposing it into 3 factors, u, v, and w. Now, first, in case of a MapReduce implementation, mappers get the input data and partition and sort the blocks, right? And then the sorting is done based on the strata index and then the block index. Now, if it's the first iteration of that particular, say, epoch, then you get the values of the u, v's, and w's from the previous epoch. And then you run the first set of stratas are pushed by the mappers to the reducers, and then you run your SGD on them. Now, when you go to the next strata, the reducers synchronize, project among different blocks, and then the second strata is pushed, and the SGD is run, and so on. So essentially, this is a MapReduce implementation of the Fugue scheme. Now, let's look at the theory of Fugue. So the theory of Fugue says that if the noise, either due to stochasticity or projection or say anything inside the slow worker agnosticism, is martingale difference sequence, then the Fugue updates and the exact gradient descent updates would converge to the same set of limit points asymptotically. Now there are 2 key points here. One is that we are not assuming that the objective need to be convex, and the second is that it has to be martingale difference sequence. Martingale difference sequence is a stochastic sequence where the expectation is 0 given the past. So it's a very common theme that you will find in any machine learning problem, and it's easily satisfiable. So it's weaker than assuming that the noise terms are independent. And if you look at the classic stochastic gradient proof, there is a similar assumption in that paper as well. So now let's look at theorem second. So I was harping about this useful work, right? So the idea in this theorem is that when you do useful work, so you suppose you are in block I and you have updated ni data points, then the variance of parameter phi would be decreased. And how it's decreased is that you have these this variance in the previous, before you did the ni updates, minus some constant terms which are positive, plus some higher order terms of the step sizes. So you need to modify the step sizes to make these red circle terms closer to 0 and be ignored. And this leads to theorem third, where again the variance across successive sub-epochs decreases, and the variance in, say, sub-epoch n+1 is variance in sub-epoch n minus some positive term plus higher order terms which are ignorable again, which are dependent upon the higher order terms of the step sizes eta. Now this leads to decrease in variance, and why it's important is because when you are closer to the optima and you are decreasing the variance, your solution path would be smooth, and we'll see why that helps. Now Fugue, as you might have thought that it is just applicable for SGD, that's not the case. You can apply the same scheme for belief propagation and sampling. Also, Fugue is agnostic of the system that you are using. It can be done on MapReduce. It can be also done on SSP setting, which is a really cool, I think, setting which was proposed by Chirong Ho et al. In NIPS 2014. And why it's able to do all these things is because it relies on the structure of the problem for partitioning in data as well as model. We can discuss more about that philosophy offline. Now, the experimental results, let's look at the scalability of Fugue. So we have scalability in model on the top left graph, where you see we are comparing with Fugue, barrier Fugued, GraphLab, and the data parallel scheme, which is PSGD. Now, what is barrier Fugue is? Barrier Fugue is essentially you have to wait for the slower workers. You are not doing useful work. So it's a variant of Fugue. So we see that the green curve, which is our Fugue, is essentially outperforming all of them. GraphLab slowly catches up, but we are at par. Now, in terms of data, how are we doing? So in terms of data, you see that we scale all the way up to 80 million documents, but these two systems, the data parallel and Vertex program, both just fail. They run out of memory because they can't handle both data and model together. Now, in terms of machines, how are we doing? So in terms of machines as well, you see we scale well in all the way up till 96 machines, and the plot follows a similar pattern, which is a very normal thing to see in distributed systems as the plot flattens out. So we outperform in terms of machines as well. Now, in case of speed, as we saw this thing earlier, the plot earlier, where we were like 25 times faster, but strictly speaking, in the worst case, we are at least 3 to 4 times faster compared to our closest competitor. This is the bottom left-hand plot is for the speed in terms of exact time. Now let's look at the experimental results. Now this is where the variance reduction helps a lot, and I want to drive this point home. If you look at the network decomposition problem, you see GraphLab oscillating very wildly, and you see the plots for Fugue, they are quite stable. Similarly, the case is for dictionary learning. The top left plot, there as well you see a lot of oscillations, but our Fugue seems to perform well. And similar is the case for topic modeling. Now, let's recap and what are the key points. So it's a flexible scheme for ML problems. As I said, it's generalizable. It partitions both data and model together for efficiency and scalability. When waiting for slower machines, we run extra updates on old data again. And there's an interesting point here. We are solving a system challenge using statistical innovation. Essentially, slow worker problem is a distributed system problem. And we are solving it using statistical theory, which I find fascinating and which I think this esteemed audience should look into, because we have, in the era of big data, we have this interesting overlap between system and statistics, and which I think should be exploited. Now, for your information, Fugue Petuum is a highly scalable, fast, and theoretically grounded system for large-scale learning. And Petuum uses Fugue, so if you think this is a good scheme that we have developed, then you should go out and check this. Thank you for your attention, and I'll take questions now.